Finding the first generation of stars created in the universe has been one of astronomy's most difficult tasks. Our current cosmological models predict that these stars developed less than 1% of the universe's age, or just 100 million years after the Big Bang. Time and time again, efforts to locate these elusive celestial planets have come up short. However, a group of astronomers has now produced a groundbreaking finding that offers verifiable proof of the imprints left by the very first stars to emerge in the cosmos. Therefore, how did astronomers recognize the first batch of stars? What cues did they employ to set them out from the numerous others that are scattered throughout the night sky? The most crucial question is why this discovery is so significant to physics and astronomy. Let's consider the seriousness of the situation before moving on to the discovery. The observable cosmos contains an estimated trillion stars, which is a staggeringly enormous amount. This estimate comes from the European Space Agency. There are more stars in the cosmos than there are sand grains on Earth, according to a statement made by Carl Sagan. And according to latest calculations, the universe contains an astounding 10,000 stars for every grain of sand on Earth. In light of this, how is it even feasible to identify the very first stars or their remains in the universe? Chemistry is the solution. The Big Bang hypothesis states that primordial nucleosynthesis started 3 seconds after the universe's creation. 20 minutes passed throughout it. Only the hydrogen and helium nuclei of the primary chemical elements were produced during this brief time. The first generation of stars, known as population 3 stars, were created from these two elements about 100 million years later. These big stars swiftly converted helium and hydrogen into heavier elements in their core. In astronomy, every chemical element other than hydrogen and helium is referred to as a metal for the purpose of simplicity. As a result, the cores of population 3 stars fused metals like carbon, oxygen, neon, silicon, and iron, among others. These star supernova explosions added these heavier metals to the interstellar medium, enriching it. The following generation of stars, known as population 2 stars, emerged from this enriched medium. They already included a disproportionately larger amount of heavy chemical components. They were quite metallic, to put it briefly. These stars eventually died and were replaced by population I stars, which have the highest metallicities and are rich in metal. A population I star is best exemplified by the Sun. As a result, we now know what to search for. Only a few years younger than the universe itself, the first generation of stars, or population 3 stars, are exceedingly old. They are deficient in metals and heavy chemical elements. Additionally, they emerged at a time when the cosmos was almost 30 times hotter and denser than it is now. Being up to 100 times more massive than our Sun, they must have burnt extremely hot and brightly as a result. Astronomers have not yet observed any of these stars, despite having a strong idea of what they would look like. This is due to 2 factors. First off, the majority of population 3 stars have already reached the end of their lives, using up all of their nuclear fuel in a few of million years before exploding in spectacular supernovae. Second, even if these stars are still present, they are extremely dim and challenging to view with modern equipment. Only by using gravitational lensing can we have any chance of seeing them or their remains. Background objects may be greatly magnified due to lensing. This allows us to see things that, with our existing technology, would be hidden from view. When the Hubble Space Telescope observed Earendel, the universe's most distant star ever found, it made one of these discoveries. Even while it appears to be very impossible to observe the initial generation of stars, there is at least a method by which we can locate the remnants of them scattered throughout the cosmos. And to do this, we must research supernovae. A big star that undergoes a Type II supernova often leaves behind a dense remnant, like a neutron star or black hole. First-generation stars, though, may see a different outcome. They can blow everything outward in an expanding cloud when they supernova, leaving no stellar remains behind. Apparent stability supernova, a theoretical sort of supernova that is only theoretically feasible in the most massive stars, is what this kind of explosion is known as. Supernovae from first-generation stars are thought to have been vital in supplying the early interstellar space with heavy elements, which were then used to create planets like Earth and enable the advent of life as we know it. The remains of these explosions could be a crucial tool for astronomers researching population 3 stars to understand more about these old stars. However, over time, it's possible that the light from such massive explosions has faded into the distance, leaving us with only a diffuse cloud holding a complicated mixture of materials to study. However, as has been shown in other investigations, even such a cloud can disclose a wealth of information. Astronomers can learn more about the conditions in the early cosmos by deducing the processes that generated the elements by examining the chemical makeup of such clouds. As a result, even though it may be impossible to observe first-generation stars directly, their explosion remnants provide a special window into the early history of the universe. And with the most recent discovery, a similar strategy was employed. Astronomers studying the second most distant quasar discovered to yet with the 8.1-meter Gemini North Telescope in Hawaii recently made an interesting finding. With a measured redshift of 7.54, this quasar also houses the second most distant and oldest supermassive black hole. The Gemini near-infrared spectrograph, which divides the light emitted by astronomical objects into constituent wavelengths that carry precise information about the elements present, was used by the researchers to explore the region around this quasar. One of the only telescopes of its scale with the tools required to conduct such observations on Earth is Gemini. The scientists employed a chemical abundance estimation technique based on the observed UV radiation to examine the spectrographic data from the clouds surrounding the quasar. Additionally, this technique is sensitive enough to detect a very low magnesium to iron ratio. The team improved it to the required redshift value of 7.54 even though it was initially designed for quasars at a redshift of up to 3. According to their investigation, the iron to magnesium ratio in the material surrounding the quasar was nearly 10 times higher than it was in the Sun. Additionally, the iron abundance itself was 20 times greater than the iron abundance in the Sun. These results offer crucial insights into the chemical development of the early cosmos, indicating that the first stars in the universe probably produced a lot of heavy elements like iron. The mainstream theory of chemical evolution was put to the test because the ratio of iron to magnesium was far higher than what would be anticipated from ordinary supernovae. However, the debris left behind by an all-consuming explosion of a large first-generation star with a mass of between 150 and 300 solar masses could account for this ratio. In other words, we have discovered the remains of a population 3 star from the rare first generation of stars that formed in the early universe, as only a pair instability supernova is known to produce such debris. This discovery offers intriguing proof of first-generation stars and may provide insight into the development of matter in the universe. Stars can offer significant hints about the beginnings and development of the universe as they get older. The cutting-edge capabilities of the James Webb Space Telescope will allow astronomers to examine even the most remote and ancient objects in the cosmos. Researchers can learn more about the conditions present throughout the universe's early history and how it has changed over time by examining the chemical makeup of these items. Recently, astronomers found a brilliant comet heading towards Earth. When it passes by our planet, it might be brighter than some of the most prominent stars in the night sky. Make sure you watch this episode if you missed it to learn more about this fascinating finding.